Hello, everyone. So, today we shall be considering a topic electric field. And in this topic, we'll be looking at Coulomb's law, electric field intensity, electric potential, capacitor, and capacitance. All right. So, let's dive in. Now, I'm talking about electric field. You're like a football field. A football field is a region where football is played. So, the same thing applies to electric field. Electric field is a region where electric force is felt. So any region where you can feel the force of electricity is known as electric field. And the common one we are familiar with in layman language is the transformer. Now, when you go to the transformer, you will see a boundary placed around it that out of bounds, because that boundary is full of what? Electric field. Anyone that enter into that field will be affected. Okay, so an electric field is a region where electric force is felt, and it is a vector quantity because it has magnitude and direction. Okay, now the direction of the field can be determined using a test charge. Okay, a small positive charge. If you want to know if a electric field is an environment or a region, you use a small positive test charge to confirm that. Okay, now I will say that let's talk about different way or different type of electric charge. Okay, we have just two type of them: the positive charge and the negative charge. Okay, now the positive charge normally generate a charge inward, from inward to outward. You could see the arrow. So if it's a positive charge, its field go from in to out, like this particular one here. But if it's a negative charge, the charge exhibits its field from out to in. Okay, that's how electric field is being generated. If it's a positive charge that is generating the field go from in to out. But if it's positive, if it's a negative one, it go from out to in. Now let us imagine a situation where you have this positive charge and this negative charge brought together. That takes us to the law of electrostatic. The fundamental law of electrostatic says that like charges repel, unlike charges attract. Now in this case, they are unlike charge because one is positive and the other one is negative. Now that they are together now, the field they generate result into this diagram we have here. If we pay a closer look to this diagram, you will see that this orange one is a positive charge, while this blue one is the negative charge. And you could see that the positive charge is generating its field, and this field is being attracted by the negative charge. So at the end of the field, you could see the direction of the electric field. They are attracted to each other. The positive one generates its field and it goes to attract the negative one. So this is what the unlike charges attracting each other. But let's come to a scenario like this where you have two positive charge. The first positive charge generates its field and the second negative charge generates its own field too. At the end of the day, you find out that their field are repelling each other because light charges repel. So the field are repelling each other, and this space where the left untouched is called the neutral point. Neutral point is a region in the electric field where electric force is not felt because there is a strong repulsion occurring in that region. So when it is light charges, the field repel each other, and there will be a neutral point. Okay, so those are the ways at which electric field are generated. We have the isolated positive charge. This one we talked about earlier. And we have the isolated negative charge. Then we talk about unlike charges attracting each other and light charges repelling each other. All right. So having known that, we then need to know the law that guides this attraction or repulsion of electric charges, and that law was propounded by Coulomb, a scientist called Coulomb. And what does the law state? The law states that in a given medium, the force of attraction or repulsion between two charges is directly proportional to the product of the two charges and inversely proportional to the square of the distance between the two charges. Okay, what is that law saying? Let's briefly look at this diagram here. Now, this is one charge Q1. This is another charge Q2. Now, the charge Q1 has a charge value of -4 microcoulomb, while charge Q2 has a charge of 8 microcoulomb. Because this might not show that it is what a negative charge, while this one shows that it's a positive charge. And remember the law of what? Fundamental law of electrostatic, that unlike charges attract. So these two charges, Q1 and Q2, are meant to attract each other. And that is why by the time I move this charge close to this, you see this arrow here going to that direction, and this arrow pointing to the same direction, because there is a what? There's an attraction occurring. You can see the two arrows pointing towards each other because there's an attraction. Now, what Coulomb's law is saying is that as we are moving the charges close to each other, you could see that the force between them begin to increase. This is 995.161 Newton. But by the time I increase the distance between the two charges, what happened to the force? You see that it was gradually reducing. As I go backward, the more reducing the distance between them, gradually reducing. And that is what the law is stating. It's stating that this force, okay, that is acting between two charges is directly proportional to the product of these two charges. Like now, product in multiplication, 4 times 8, okay, that's 22. Now, if you increase the value of this, maybe from 4 to 6, and multiply it by 8, the product will increase. That increment in the product also affect the increment in the force acting on them. But by the time you reduce the distance between them, the force increase. So that law is stating that the intensity of its force increases as the product of the charges increases, while the intensity of the force also reduces when the distance between them increase. When the distance between them reduces, you see, when the distance between them reduces, the force between them increase. You could see, and when the distance between them increases, the force between them reduces. You could see it now. It's also reduced. That's what the law is stating. All right. So in a nutshell, the force acting between two charges is proportional to the product of the charge and inversely proportional to the square of the distance between them. All right. So let's go back to what we are saying. So mathematically, F, which is the force acting, is equal to KQ1 Q2 over R squared, where the K is a constant and it has a value of 9 times 10 to the power 9 Newton meter square per coulomb square. And of course, the K also is represented with 1 over 4 pi epsilon naught. The epsilon naught is also a constant, that is 8.85 times 10 to the power minus 12 per Newton per meter square coulomb square. Or in another way, it is 8.85 times 10 to the power minus 12 farad per meter. Either of them is correct. They are just a constant that we should know. But now, if you look at the value of K again, we say K is 1 over 4 pi epsilon naught. If you now come to equation 1 and replace the value, if you replace the value of K in equation 1 with 1 over 4 pi epsilon naught, then we have a new equation here, which is F equals to Q1 Q2 all over 4 pi epsilon naught R squared. So this is the equation for Coulomb's law. So let's take note of that. All right, now let's talk about what we call permittivity of free space, which is obtained with epsilon naught, and relative permittivity. Permittivity of free space is defined as the capability of a vacuum or free space to permit electric field. You know, a free space or a vacuum is a space where that nothing exists, or maybe the only thing you could find there is air. Now, the ability of that space to allow electric field is known as what? Its permittivity. All right. So it's obtained with epsilon naught, but we also have what we call the relative permittivity, which is epsilon r. The epsilon is a Greek symbol. This relative permittivity of a medium is just the ratio of the permittivity of a medium to that of air. In other words, relative permittivity epsilon r is equal to what? Epsilon m over epsilon naught. Why the epsilon m represent permittivity of a medium and the epsilon naught represent permittivity of free space or air. So by formula, relative permittivity equals epsilon m over epsilon naught. All these terminologies are important in understanding this concept of electric field. All right. So having talked about that, let's move to what we call the electric field intensity or strength. Sometimes we call it electric field strength. Sometimes it's known as electric field intensity. And its own symbol is capital A. What is it about? It is defined as the electrostatic force experienced by a unit positive state charge at that point. And it is a vector quantity. Its unit is Newton per Coulomb. So by formula from that definition, we could say that electric field intensity equals force over charge. Okay, F over Q now, where the Q is the charge, F is the force. Okay, but we know that our F itself from Coulomb's law is Q1 Q2 over 4 pi epsilon r squared, where our Q1 is now capital Q, our Q2 is now Q naught. Now, if you now replace the value of F, this value of F into equation 1, then we'll be having electric field intensity to be Q all over 4 pi epsilon naught r squared. But we also know that 1 over 4 pi epsilon is K. So another way of writing electric field intensity is what? KQ over r squared. All these formulas are expected to be known. That's why we're introducing them. Aside this terminology, another thing you need to know in electric field is called the electric potential. The electric potential at the point is the work done in bringing a unit positive charge from infinity to that point against the electrical force of the field. Okay, so the work done in taking a charge, a positive charge, from infinity to another point against electrical force of the field is called the electric potential of that charge. And of course, it is measured in joule, and it is a scalar quantity. So by formula, V, which is the electric potential, is equal to what? Work done all over charge from the definition. Another way of defining electric potential is electric potential at a point due to a charge at the distance r from that charge is given as KQ over R. Okay, that's another formula. Aside from this one here, another formula for electric potential is what? KQ over R, where our K is still our universal constant for electric field, and then the Q is the charge, the R is the distance between the point of infinity to the point where the charge is taken to. All right. So having known this concept electric potential, then we move on to capacitor and capacitance. Of course, the capacitor is a device for storing electric charge or for storing electricity. We use it to store charge. That's the main function of capacitor. And the ability of this capacitor to store charge is called capacitance. But that's a layman definition. by the real definition of capacitance, we say it's defined as the ratio of the charge on the plate to the potential difference. Now, this is a typical example of capacitor. They come in different ways, but whatever way they may come, they always have one thing in common: two legs, and what we call it plate. They have two plates. Okay, some have positive and negative plates. Okay, some you can't really, anyone can be positive, anyone can be negative. If one is positive and the other one is negative, you say the capacitor is polarized. That means each particular leg is meant to be positive and the other one is meant to be negative, then it's a polarized capacitor. But if anyone could be positive and negative, then it's not polarized capacitor. So it can come in different form. All right, but whatever way it may come, they have positive and negative plates. Now, by formula, capacitance, which is represented with C, is equal to charge over voltage. Another formula for capacitance is what? Is epsilon A over D, where the epsilon is a constant, the A is the area of each of the plate, and the D is the distance between the legs of the plate. All of these are key that we know in solving problems involving capacitor and capacitance. All right. Now, these capacitors can be arranged in two major ways, either in series or in parallel. Now, the diagram here shows that they are arranged in series. When they are arranged in series, you could see that they are placed side by side in the sense that the positive plate of C1 is connected to the negative plate of C2. Same also, the negative plate of C2 is connected to the positive plate of C1. When capacitors are connected that way, we say that they are in series. On the other hand, they can also be connected in parallel. When they are in parallel, we connect all the positive plates together. For example, the positive plate of C1, you could see here, is connected to the positive plate of C2, and positive plate of C3 is also connected to the positive plate of C2 and C1. So all positive plates are connected one side, all negative plates are connected the other side together. In this connection, we say it is parallel connection. So when they are in series, to calculate their total capacitance, you say 1 over Ct is equal to 1 over C1 plus 1 over C2 plus 1 over C3. That's the formula for calculating total capacitance when capacitors are in series. But when they are in parallel, their total capacitance, which is Ct, will be equal to C1 plus C2 plus C3. Another concept you need to know about a capacitor is to know the work done by the capacitor. And the formula for work done is half CV squared, where the C represents the capacitance of the capacitor, the V represents the voltage or the potential difference. Aside from this formula for work done, another formula is what? Half Q squared all over C. The Q represents the charge stored by the capacitor, and the C represents the capacitance of the capacitor. Sometimes we call this work done potential energy of the capacitor. So this is just all that we need to know about the concept of electric field. So we are going to throw the curtain here till I come your way again. Thank you for listening. Bye for now.